Hey everybody. Today I'm doing another example computing a Taylor series. So remember that a Taylor series expansion of a function is just a power series for that function at some particular center, x equals a. The way we compute the coefficients of that power series is by taking derivatives of the function at that value a and then dividing by n factorial. Okay. The problem we want to tackle here is f of x equals xe to the x minus 1. We want a Taylor series expansion at x equals 1. We're also going to want to determine the interval of convergence once we have that expansion. In other words, the domain on which that power series is valid. So we got to take some derivatives. In this case, it's a product rule. Derivative of the first times the second plus the first times the derivative of the second. Let's simplify that a little bit by factoring out e to the x minus 1. Second derivative involves another product rule, and there's an identical simplification. I'm already starting to see a pattern here, but I'm going to do one more derivative just to be safe. Product rule, factor out e to the x minus 1. Okay, so now I'm seeing the pattern. The first derivative has an x plus 1, the second has an x plus 2, and so on. So the nth derivative is going to be x plus n times e to the x minus 1. And of course, when I plug 1 into that, e to the 0 is 1, so I just get n plus 1. Now let's go back to our original formula for our Taylor series expansion using the fact that the nth derivative of f is n plus 1, at x equals 1, of course. Plugging that in, I get the Taylor series n equals 0 to infinity, n plus 1 over n factorial, x minus 1 to the n. Here are the first few terms. So we aren't done until we find the interval of convergence, of course. And we do that using the ratio test, as always. I'm going to take the ratio of adjacent terms. So I go back to that power series, I plug in n plus 1, and then I divide by what I get when I just use n, and simplify by multiplying by a reciprocal of the denominator, and start canceling things. So, of course, almost all of the factorials go away. I'm just left with an n plus 1 in the denominator. Almost all of the x minus 1s go away. I'm just left with x minus 1 in the numerator. Finally, I'm left with the n plus 2 over the n plus 1. So overall, here's what I get. Now, x is just some fixed number, so that's not going to affect convergence. I'm really looking at the limit as n goes to infinity of n plus 2 over n plus 1 squared. And that's a rational function where the power in the denominator is greater than the power in the numerator. So it's going to 0. Overall, this limit is 0. So the ratio test says that whenever this limit is less than 1, I get convergence. But the limit's always 0, always less than 1. Therefore, the series is going to converge for all values of x. To say it slightly differently, the radius of convergence is infinity in this case.